Hello students, in lecture 18 of Calculus of Variations, here we will discuss yet another method to solve a given partial differential equation with certain boundary conditions. In such a situation, we can find the approximate solution of that partial differential equation using this method. The method is Kantorovich method. We also discuss some examples regarding this method. And exercises here, I'm not going to give the separate exercises. The same exercises which we have given in lecture number 17, you can solve those exercises with the help of Kantorovich method. Because here we are using this Kantorovich method as an alternative to the Rayleigh's method. Because purpose of both these methods is same. Both these methods are used to find the approximate solution of ordinary boundary value problem and a boundary value problem in partial differential equations. Kantorovich method is found to be more appropriate than the Rayleigh's method in the sense that we find the approximate solution more closer to the exact solution of given boundary value problem. After this, we shall discuss the concept of central field and proper field. So first, the Kantorovich method to solve the partial differential equation. The problem statement is same as we have given in last lecture 17, and the problem was solved with the help of Rayleigh's method. This is the given partial differential equation. In simplified form, we write it as P uxx, P uyy, Q uxy, and R. P, Q, R are also functions of x or function of xy both. So in this situation, again, as in case of Rayleigh's method, first we obtain the functional corresponding to the given boundary value problem, of which that one equation number 1 becomes the Euler equation. The general functional form for such a problem is given by equation 2. Now to find the approximate solution of the boundary value problem, we assume a trial solution such that the boundary conditions are satisfied. So here is change in this equation 3, or in the choice of trial solution. In Rayleigh's method, usually we consider a trial solution in terms of certain constants and functions, but here we are choosing it as a trial solution in terms of a function of single variable and the functions of two variables. This fix is unknown function. Basically uix satisfies the given boundary conditions and fix are the unknown functions, and they are also chosen in some special manner. And let us discuss the whole method with the help of numerical example, so it will be more clear. Example 1. Solve the following Poisson equation in a square. The Poisson equation is uxx uyy equal to -1, mod x less than equal to 1, mod y less than equal to 1. The value of u is given to be 0 at x equal to plus minus 1 and at y equal to plus minus 1. So it is the same question which we have discussed in lecture 17, and in that lecture we have given the proof of this question, this solution of this boundary value problem using Rayleigh's method. So we are talking in a square. Here x minus 1, x is plus 1, and this is 0, y 1, and y is minus 1. So on the boundaries, the value of the function u is equal to 0. So in this case, we will be choosing the trial solution in such a manner that boundary conditions are satisfied, and here we will consider a function of x only. F x is to be determined in such a manner that f of plus minus 1 is equal to 0. And you can easily see the trial solution. In this trial solution you can see that boundary conditions are satisfied. Suppose you are writing here y equal to plus 1 or minus 1. So y equal to plus or minus 1 will give you 0. And when you put x is equal to plus minus 1, so you will write here plus minus 1, so that will be 0. So why we are taking this function in such a manner? Only then this u will be able to satisfy these given boundary conditions. That is why this fx should be determined in such a manner that f of plus minus 1 must be equal to 0. Now we form the functional as usual by substituting the values of u, ux, uy in, and value of p, q, r here. Value of p, q and r here, we get this functional. And from this functional, when we substitute value of ux, uy and 2u and u here, we get this type of form. Ultimately, after first we are integrating it with respect to y and substituting the limits of y from minus 1 to 1, we get this type of expression. Now here it becomes again a functional where we have this f as dependent variable and x as independent variable. So in this situation we can consider this f equal to 2 by 5 f dash square plus f square minus f. So you can see in place of y here small f is appearing, and corresponding to this we can see the Euler equation becomes, actually it is curly f over curly y, so we write here curly f for small f minus d by dx of curly f over curly y dash equal to 0. So when we substitute the values, you can see curly f over curly f here, it gives us 2f minus 1. So corresponding to this term we are having this, then d by dx curly f over curly y dash, this gives us 2 by 5 to f dash equal to 0. Further simplification gives us 2f minus 1 minus 4 by 5 here, and derivative of this is f double dash equal to 0. So consequently we get this equation here. So in fact using this we get Euler equation in this way, and from after solving this we get the value of f in such a manner, because here we are having f double dash minus 5 by 2f. This is f double dash, yes. On simplification we are getting f double dash minus 5 by 2 f equal to minus 5 by 4. So this is in fact d square f by dx square minus 5 by 2 f equal to minus 5 by 4. So here if you try to solve it, the auxiliary equation becomes d square minus 5 by 2 equal to 0. So d equal to plus minus under root 5 by 2. So the complementary function becomes in this situation that c1, you can say c1 cos c1 e raised to power 5 by 2 x plus c2 e raised to power minus root 5 by 2 x. We can write it in this manner, and we find the particular integral. Particular integral in fact is 1 by d square minus 5 by 2, and this is equal to into minus 5 by 4 and e raised to power 0x. When we put d equal to 0 here, so it becomes minus 5 by 4 divided by minus 5 by 2 and into 1. So 5 with 5, minus with minus, so this is in fact 1 by 2. So the solution is fx equal to complementary function plus particular integral. So in fact, particular integral is 1 by 2 and complementary function is c1 e raised to power root 5 by 2 x plus c2 e raised to power minus root 5 by 2 x. So in fact, this is value of fx. But here you are given that the value of fx is this one. It is easy to express this function in this form. Rather, you can keep this function in the simplified form. How we can convert? We can convert this exponential function in terms of the hyperbolic functions. So we can write in this manner also, solution in this manner in terms of hyperbolic function or also in terms of exponential function. So if we are writing it in the hyperbolic functions form, then using the boundary condition f plus 1 equal to 0 and f minus 1 equal to 0, if you apply the boundary condition here, you can get the values of these constants a and b, and consequently you can get the value of function fx. Once you get the value of fx, you can substitute the value of fx in the trial solution you have assumed, because we have assumed the trial solution u equal to 1 minus y square fx. So you substitute the value of fx over here and we get the final approximate solution like this. Here u of xy equal to 1 by 2, the whole thing fx, 1 minus y square. So from which if you put 0, 0, you will get value 0.303. Now, as we have seen in case of related method, the related method gives the value of 0, 0 is this, but the exact value in fact is this one. So from these comparisons, you can see that the approximate solution obtained due to this Kantorovich method is more closer to the exact value, because that is 0.303 by Kantorovich, and this value is 313. So I think this 303 is more closer rather than this 0.313. So that is why a Kantorovich method is superior to the Rayleigh-Ritz method. We again consider the similar problem as discussed in the Rayleigh-Ritz method. The same problem we try to solve using the Kantorovich method to solve the following Laplace equation. The boundary conditions are given like this. So as usual, in this case, the functional becomes this: j equal to minus 1 to 1, this double integral ux square uy square dx dy. Now here we again assume the trial solution in such a way that boundary conditions are satisfied. So suppose how this condition will be satisfied. You can see if you put x equal to plus minus 1, it must gives you 1 minus y square. So that means this fx must be chosen in such a way that this f of plus minus 1 gives you 1. Only then, when it is 1, only then this u of plus minus 1 can give you 1 minus y square. So similarly here also, if you write y equal to plus minus 1, x whatever, then this condition is satisfied. So both these conditions will be satisfied if you choose the trial solution in such manner. So j becomes, after substituting the value of ux, uy, we get this situation. So as we have proceeded in the last example, we get value of j in this manner, because after integrating this with respect to y and substituting the limits, it becomes a function of f and f dash only here. So now in this case, f becomes 2 by 5 f dash square plus f square, and corresponding to this, the Euler equation is this one, and f of plus minus 1 is 1. So solving these, we get value of f equal to this, which is the required solution, and this is value of fx in fact, and then we put value of fx in the trial solution. We have assumed we get this approximate solution. So u of 0, 0 in this case gives you this thing, and we compare it with the exact value 0.414, 0.411 and value 0.375 by Rayleigh-Ritz method. So we can see in this case also the method of Kantorovich give the solution more closer to the exact value rather than the Rayleigh-Ritz method. So similarly, the next example is regarding the estimate of least eigenvalue of this Poisson type of equation, and these are the boundary conditions given over here. We will proceed in the same manner. In this case, the functional becomes this j, and we take the trial solution in this manner so that f of x plus minus 1 equal to 0. Why we are taking it 0, we have already explained in the earlier examples. Now we obtain from here this type of expression. So we integrate with respect to y, substitute the limits from minus 1 to 1. Finally, we get this type of equation. Now the Euler equation corresponding to this by choosing f equal to f dash square plus 5 by 2 minus lambda into f square. If we choose f like this, and then Euler equation gives you this form. When you simplify this, you get value of fx, and when you substitute f plus minus 1 equal to 0, it gives you b equal to 0. So when b is 0, then writing 0 on this side and a cos of this thing, then either a is 0 or this is 0. If you consider a equal to 0, that will give you the trivial solution or the 0 solution of the equation. Therefore, for a non-trivial solution, you have to assume cos of this quantity equal to 0. But you know, when you have cos of theta equal to 0, that can happen only in the situation when theta is equal to 2n plus 1 pi by 2. So for simplicity, if we take n equal to 0, so you can say theta equal to, in this case, will be pi by 2. So therefore lambda minus 5 by 2, because for the least value, in fact, we are taking for least value. So theta is pi by 2. So we have written over here this cos of this quantity in place of theta is this thing actually. So this is equal to pi by 2. Simplifying this, we get lambda equal to 5 by 2 plus pi square by 4. Simplifying this, so we get the least value of lambda is 4.967. So next is the concept of proper field. What is the meaning of proper field? If we have a family of curves given by y equal to y of xc, c is in fact the parameter. We go on changing the value of c, we can get the family. If we have this family of curves, then it is said to form a proper field in a given region D of xy plane if one and only one curve of the family passes through every point of the region D. So example is here, inside the circle C, suppose the region is given to be a circle whose center at origin and radius is 1. And inside this circle, suppose we are assuming a family of parallel lines given by this. So obviously in this family, this C gives the intercept on the x-axis, intercept of this line on the x-axis. So if we visualize this family of lines within a circle, then what kind of situation we can have? This is the situation. This is the circle, x square plus y square equal to 1. This is origin and radius is 1. Now if we go on changing the value, we are given the family like this, y equal to x plus c. Or I can write in this manner that x minus x plus y equal to c, or I can say x over minus c plus y over c equal to 1. So that means we have a line in general, we have a line whose intercept on x-axis is minus c, and intercept on y-axis is minus c, and intercept on y-axis is c. So equation will be like that. If we go on changing the value of c, suppose this is 1, so this is one line. If we take it as c equal to 2, then line becomes like this. If 3, like this. And we go on changing the value, the family of lines comes like this. So that is, you can see, appearing in this circle. Now in this circle, if this is the family of line, then you can see the circle has the region D enclosed within it, and every member of this family means family of lines, is passing through exactly one point of the circle. This is passing through this point, this point. Through this point, only one member is passing, not the other one. For example, this point, only one member is passing, not the other one. So in such a situation, you can say that this family, this family of parallel lines forms a proper field, since through any point of the above circle there passes one and only one straight line of the family as shown in figure 1, means this one. On the other hand, if we consider a family of parabolas inside the same circle, then it does not form a proper field. Why? Because the situation becomes like this. You change the value of c, the parabolas becomes like this, and you can see, suppose you have this point, then two parabolas are passing through this point. Suppose this point, you have this point, this point. So from through these points, more than one member of the family is passing through. So that is why this type of family of parabolas does not forms a proper field in this circle. So it's shown in figure 2. Next is the central field. What is the meaning of central field? If all the curves of the family y equal to y of xc pass through a certain point x naught y naught, suppose this is the point x naught y naught, if all the members are passing through this particular point only, this forms a pencil of curves because it becomes like a tip of the pencil, then they do not form a proper field. So if such a family exists there, then they do not form a proper field in the region D. Now, suppose we have the region like this. If we draw the region D like this. Now this is the region D. Now you can see the tip of the pencil is outside the region D. So in that situation, you can say that this pencil forms a proper field in the region D. So that is the case. If the center of the pencil belongs to D, however, if the curves of the pencil covers the entire region D and do not intersect anywhere in this region. For example, I have explained here. If they within this region, the curves are not intersecting, so they are forming a proper field. They are forming a proper field. So you can say the family y equal to yxc is said to form a central field as shown in figure 3. You can see here, because they are here. Next example, you can see the pencil of curves y equal to a sin x when a lies between 0 and a is less than pi forms a central field, but forms a proper field in the sufficiently small neighborhood of segment of x-axis for this condition. Further, the pencil of curves does not form a proper field in the neighborhood of segment of x-axis with this condition. So everything can be visualized in this figure. First, we are talking about that this pencil of curves, if you draw it, if you draw the curve, then we will have this type of situation. When we have x lies between 0 and a, when x is between 0 and a, and here we have x equal to a, means this line is x equal to a, and here we have 0. When x is lying between 0 and a, in this case you can see this is the tip, and all the curves are going through up to this. So in this part you can say it forms a central field because all the curves are meeting at a point or emerging from this one point, and it becomes the tip of the pencil. That is why in this region it forms a central field. Now if I exclude this tip and I draw a line here at a distance delta from this y-axis. Now for this reason I can say, for this reason, this x lies between delta, for this part x lies between delta and a. When in this part you can see we are having, in this region, through every point only one member of this family is passing. Therefore for this part it is forming a proper field. Obviously here x lies between this, delta is something greater than 0, some number, and a is less than pi, because when you take x equal to a is equal to pi, so that case this has to be there, and at that situation these curves merge over here. So that is why in this part it is forming a proper field, and from here to here when x lies between 0 to a it is forming a central field. And further, if we take the line x equal to a1 here, x equal to a1, and this a1 is greater than pi, means we are going beyond this point. Here this is pi, in fact here it is 0, here it is pi. If we are going beyond this point, means a1 is greater than pi and x lies between 0 and a1, that means now x is lying between 0 and a1 up to this place. So now for this you can say it is not forming a proper field, because through one point here more than one curves are passing. Neither this is the case of the central field, neither it is the case of proper field. So you can say it is not forming a proper field for this reason. That is it about this lecture. So thank you.